So in this video, we're just going to have a look at the Winkler method, which is the titration that we use to work out this biochemical oxygen demand. Now I have a timestamp here on the right hand side, just to show you some details. So at 104, a couple of things is you don't put air in the bottle. Make sure that you fill it with water completely to the brim. The next particular one that we're going to be looking at is 131, where we're going to add manganese sulfate solution, and I'll explain why we're doing that now. So why do we add the manganese 2 sulfate solution? So first of all, when we're looking at manganese 2 sulfate is MnSO4, and that consists of Mn2 plus ion and an SO4 dinegative ion. So adding manganese sulfate is going to supply us with these ions here, the Mn2 plus and the SO4 dinegative. The one we're interested in is the Mn2 plus. Then at 149, on top of the manganese sulfate, we add alkaline potassium iodide. So that goes in next. So what's the purpose of the alkaline potassium iodide? Now in here we've got a lot of chemistry in here. Let's have a look at it. So when we add the alkaline potassium iodide, what is alkaline potassium iodide first? Well, it's a mixture of potassium iodide, which is Ki, and we also add in NaOH. NaOH is a strong base, and that gives it an alkaline pH. So this is where alkaline potassium iodide comes from. Now again, remember a couple of things. Your NaOH, when it's put into solution, will release Na plus ions and OH minus ions. The same thing would happen with the potassium iodide. So let's see what happens. Remember what we've got. We've got Mn2 plus now in the water. That comes from your manganese sulfate. We now have OH minus, which comes from the NaOH that we've just added as part of our potassium iodide. And the Mn2 plus from the first addition and the OH minus from the second addition will form MnOH2. Now, this is a precipitate, and it's a white precipitate. Now, when you add these two into the water, it's very, very difficult to actually see the white precipitate. You don't see it too often. Now what we've got in solution is MnOH2. This is Mn2 plus ions. So if you take MnOH2 is Mn2 plus, and you also have OH minus ions, but of course you've got two of them in order to balance this out. So we're dealing with Mn2 plus ions. Now if we scroll down, so now that MnOH2, the precipitate, has been formed inside the jar, that's where we're going to continue from. MnOH2, and I've balanced the equation here. So the MnOH2, which has just been formed, that reacts then with the oxygen that's dissolved in the bottle, and it also reacts with the water that's in the bottle, the 2H2O, and you end up forming MnOH3, which is the brown precipitate that you saw in the bottle. And again, in this MnOH3, we have Mn3 plus. The reason why is because OH is minus, and if you've got three of those, Mn3 plus has to be formed. The Mn3 plus gives us the brown color. So now we've got a brown precipitate formed. So let's just have a look at that brown precipitate being formed. Okay, so that's your brown precipitate formed. So what's next? It's just a note about the brown precipitate. Some experiments, brown precipitate will not be formed. And if there's no brown precipitate formed, that means there's no oxygen in the sample. Because again, if there's no oxygen in the sample, the reaction can't occur for the MnOH3 to be formed if there's no oxygen. So an example of this would be water that's boiled, which has no oxygen in it. Or if this is highly polluted water, where you would also have no oxygen in it as well. If we move on to 3.31 or 3 minutes 31 seconds, we're going to add some acid to the solution. Let's have a look at that. So 3:31. So here we can see after the sulfuric acid has been added, the precipitate disappears and we're left with this kind of a reddish brown substance. So let's have a look at the chemistry behind that, what's happening. So the whole point of this and the red-brown colour is the fact that iodine is being formed. So here's the equations for it. So we're starting here with our brown precipitate, which is MnOH3. And already what's in the bottle is iodide. So we put potassium iodide, alkaline potassium iodide in the bottle earlier on. And again, when potassium iodide hits the liquid, it splits up into K+ ions and I- ions. So what happens is the brown precipitate reacts with the iodine part of the potassium iodide. You then end up producing H+ from your acid, because an acid is a proton donor. So those three things together will liberate iodine. And iodine is the red-brown colour that you've seen in the bottle. You end up producing some water and some Mn2+ ions as well. The brown precipitate dissolves and a red-brown colour is seen. That implies that iodine is actually been formed. So this titration in a nutshell, the amount of iodine formed, or liberated is the word we use in chemistry, the amount of iodine formed depends on how much oxygen is in the sample. Okay? If you have more oxygen, you will have more iodine being formed. So it's very, very hard to do a titration of oxygen against something else, but we can do titrations of iodine. And as you've done before in the lab, you're going to titrate your iodine sample against sodium thiosulfate. When you titrate iodine against sodium thiosulfate, that will find the concentration of the iodine. And because the concentration of the iodine is directly linked to the oxygen, that means you're going to get the concentration of the oxygen. At 8:01, there's going to be a colour change. So let's have a look at this and explain this. So this is now into the titration. The colour change is very important in this titration because it involves using something halfway through the experiment. Watch this. So as you can see, this was red-brown. It was the colour of what's in the bottle there. And now in the conical flask, you can see it's a very pale yellow. This pale yellow is just a much lighter variation of the brown colour in the bottle. It's just a lot less iodine in it. But because it's yellow, it still has a very, very small amount of iodine in it. When you want to do a colour change in this experiment, it goes colourless. But the pale yellow is so pale that it can sometimes be very, very difficult to see it go from pale yellow to colourless, to find that point. So what we do is we add some starch indicator. Now when you add starch indicator to that conical flask, it will turn blue-black. The reason why is because starch reacts with iodine. And you've seen that before in your junior cert experiment where you would add iodine to a potato to detect starch. It turns blue-black. The reason why we do that is because it's much easier to see a colour change from blue-black to colourless than it is from very pale yellow to colourless. And that's the only reason why we add the starch indicator, is to help us detect the endpoint more easily. Common leave insert question, so make sure that you can see that. So here it is being added. And that covers the end of that particular part of the titration. So let's have a look at the last little bit here. What you're going to have is the colour change is red to brown to colourless. However, red to brown goes to pale yellow first. It's hard to see the end point. It contains a small bit of I2. You're going to add some starch solution and the solution goes blue-black. The solution then goes colourless. And that's pretty much the end of the practical part of the experiment. So now what we're going to do is we're going to have a look at some calculations. And there's a couple of things that you need to know in the calculations here. So we start off with the first example before we go into a lead insert question. In a Winkler determination of dissolved oxygen and water, 100 cm³ samples of water were analysed. The iodine liberated in the experiment was titrated against a 0.2 molar sodium thiosulfate solution. and the average titration figure was 5.7. Calculate the amount of dissolved oxygen in the water in parts per million. So before we start working out M1, V1, N1 and all the things to work out our concentration, there's a couple of things you need to know about all the equations that's happening. We've gone through all the equations up above, and you can see all the equations are actually written here in this summary. Now you can see that you've got MnOH2 plus O2, it forms the precipitate, then it forms your iodine, and then the iodine is titrated against your sodium thiosulfate, which is here, forming this particular complex here. You don't need to know the name of that. The problem with this question is when you do the calculations is to work out the number of moles. Again, we're looking at oxygen on one side, so when we eventually do M1, V1, N1 and M2, V2, N2, we're going to be working out oxygen on one side of the equation, and we're going to be working out S4O6 dinegative on the other side. But our oxygen is up here in the equation and the other one is down here. They are three separate equations. They're not one equation. So how do we work out the number of moles? Normally you would have one equation straight across and you can see the number of moles, but here it's a little bit more difficult. So what I've done is I've color coded them. So as you can see, we have, this is 1 mole, it's not step 1. This is 1 mole of oxygen will give 4 moles of MnOH3, and I have them color coded then blue. So that's a 1:4 ratio. So we've got 1:4 over here. Then on the second line, we have 2 MnOH3. 2 of these here will produce 1 iodine molecule. So that's a 1 before the iodine. There's no coefficient there. Now, that's colored in yellow. So if 2 produces 1 here, well then that means that 4 will produce 2. Right? So basic ratio and proportion. And then in green, for the last one, we can see that we have 1 iodine molecule will produce 1 S4O6 molecule. So I have that written there in green. Now we've got to combine these together. So that means 1 oxygen molecule at the top, when you work down through it, will produce 2 iodine molecules. So 1 oxygen molecule will produce 1 mole of oxygen will produce 2 moles of iodine, which in turn will produce 4 moles of S4O6 2-. Now you're going to have to go through that at your own speed, but basically all we're trying to do is work out how many moles of oxygen will produce how many moles of S4O6 dinegative. And it's 1 mole of oxygen will produce 4 moles when you work out the ratios. Now you won't be asked to work out those ratios, and sometimes in the question they will tell you what the ratio is, or you can just learn it. You can just remember that the ratio for the biochemical oxygen demand is 1:4, which a lot of students do. We'll come back, we'll have a look at the calculations there in a couple of minutes in part 2 of the video.